Have you ever just stopped and looked at, I don't know, a glass of water, the flame of a candle, or even your own reflection, and really wondered what's going on under the surface? I mean, really going on? Well, today, we're going to peel back those layers of reality. We're going to find the simple, elegant blueprint that, believe it or not, governs, well, everything.
So let me ask you this. Just imagine for a second, some huge cataclysm happens. All of our scientific knowledge, wiped out, gone. And you can only pass on one sentence to the next generation. What statement, what single idea would contain the most possible information in the fewest words to give them a head start? It's a heck of a thought experiment, right? And the answer? It's surprisingly simple, but oh man is it powerful.
And here it is, the single most important piece of scientific knowledge we possess. It's called the atomic hypothesis. And it all boils down to three simple ideas. Number one, everything is made of tiny particles called atoms. Number two, these little things are always moving. They're in perpetual, constant motion. And number three, they attract each other when they're a little bit apart, but they push away when they get squeezed too close together. And that's it. Seriously, that one idea is the key that unlocks pretty much the entire physical world.
Okay, so let's treat this idea for what it is, the ultimate survival knowledge. With just this one hypothesis, we're going to see how you could rebuild our entire understanding of nature, basically from scratch.
But before we dive in, a quick but really important point on how science actually works. Here's the deal. The only judge of what's true is experiment. That's it. Every law we think we know is really just a very, very good approximation. I mean, for centuries, we thought mass was constant. A spinning top weighs the same as a still one, right? Seems obvious. And it's a great approximation for everyday stuff, but it's not the whole truth. Turns out, as things get insanely fast, their mass actually goes up. And here's the kicker. Even a tiny correction like that can completely change how we see the universe. So with that in mind, let's get back to the most profound idea of all.
Okay, so what are these atoms really? Well, they are just unbelievably, mind-bogglingly small particles. You'll see the term angstroms on the slide. Don't worry about it. It's just a way to measure crazy small distances. To really get a feel for the scale, try this on for size. Imagine you could take an apple and blow it up to the size of the entire Earth. A single atom inside that giant Earth-sized apple would be about the size of the original apple. Just let that sink in. We're talking about a scale of smallness that is almost impossible for our brains to even handle. All right, now that we have some idea of just how ridiculously small these things are, let's see what they can actually do. We're about to go on a little journey. We're going to zoom way, way in on a single drop of water and watch how these tiny particles build the world we see every single day. Okay, so we start with a regular old drop of water. Looks totally smooth, right? Continuous. Now let's magnify it 2,000 times. And whoa, we see these little creatures, paramecia, just swimming around. But let's go deeper. Let's push it to 4 million times magnification. Suddenly, that smoothness is completely gone. It starts to look like a massive football crowd seen from a blimp. And finally, let's push it all the way to 1 billion times magnification. And there it is, the atomic reality. You can see the individual H2O molecules just jiggling and bouncing and crashing into each other constantly.
And that jiggling you're seeing? Well, that reveals the true nature of heat. Heat isn't some invisible substance flowing around. Nope. It's just the motion. It's the kinetic energy of these jiggling atoms. When it's cold, they're jiggling pretty gently. When it's hot, they're going absolutely bonkers, just smashing into each other with incredible energy.
You know, this jiggling is also what creates the states of matter. It's so cool. At low temperatures, the atoms lock themselves into this beautiful, rigid crystal pattern we call ice. They're still vibrating, but they're stuck in place. Now, add a little heat, get them jiggling more, and that whole structure just breaks down. It becomes a flowing liquid. And if you add a lot more heat, the jiggling gets so violent that they completely break free from each other and fly apart as steam. Think about that. Ice, water, steam. All the same atoms, just with different amounts of jiggle.
This constant motion also explains something like pressure. Just picture these atoms as zillions of tiny tennis balls inside a box, all bouncing off the walls nonstop. That collective banging, that's what we feel as pressure. So, what happens if we push a piston in and squeeze the gas? Well, it's just like hitting a ping pong ball with a paddle that's moving forward. The ball's going to fly off way faster, right? It's the same exact thing with the atoms. They bounce off that moving piston with more speed, which means more energy. And more energy means a higher temperature. That's literally why pumping up a bike tire makes the pump get hot. Okay, so we've got a handle on the states of matter. Let's kick it up a notch.
Now we're going to see how these same atoms drive all the dynamic processes that shape our world, from something as simple as cooling soup to the complex smell of a flower.
So, look at a covered glass of water. It seems totally still, right? Wrong. At the atomic level, it is an absolute war zone. You've got molecules constantly getting knocked out of the water to become vapor, and at the same time, vapor molecules are crashing back into the water. It's a perfect balance. It's in equilibrium. But what happens when you blow on your soup? You're basically sweeping away all the molecules that were trying to come back, so now way more are leaving than returning. And here's the clever part. Only the fastest, highest energy molecules have enough oomph to escape. So when they leave, the average energy of what's left behind goes down. The soup gets colder. You're literally letting the hot molecules fly away. This is exactly how sweating cools you down, by the way.
Dissolving salt in water. It's another perfect example of this constant back and forth, this atomic tug of war. You see, salt is just this rigid grid of positive and negative particles, and water molecules are like these tiny little magnets. They swarm the salt crystal, and their negative ends grab the positive salt bits, and their positive ends grab the negative salt bits, and they just jiggle them and pull them loose, carrying them off into the water. But at the exact same time, some of those loose salt particles are bumping back into the crystal and sticking again. Dissolving is just what happens when the pulling away process wins.
So what about something crazy like fire, a chemical reaction? You guessed it, it's the same idea, just way, way more violent. See, atoms have preferences. They like certain partners more than others. And it turns out carbon is way more attracted to oxygen than oxygen is to itself. So when an oxygen molecule gets close enough to some carbon, the atoms basically say, see ya, to their old partners and just snap together into a new, much happier arrangement. And that snap releases a huge amount of energy, the jiggling energy we see and feel as heat and light. Fire is literally just the visible result of this tiny, violent atomic rearrangement.
But it's not all just violent snapping. Think about something delicate, like the smell of a violet. That smell isn't some magical aura, you know? It's a physical thing. It's this enormously complex molecule, a very specific, intricate piece of atomic architecture. And these tiny structures get knocked around in the air until, just by random chance, one of them happens to float into your nose and fits perfectly into a receptor, like a key in a lock. It's the specific shape of that atomic key that your brain says, ah, that's a violet.
Now, you might be thinking, okay, this is a nice story, but if we can't actually see these atoms, how do we know any of this is real? It's a fair question, and one of the coolest proofs is something called Brownian motion. Picture a giant beach ball in the middle of a huge, invisible crowd that's just randomly shoving it from all sides. The ball would jiggle and jerk around, right? Well, we see that exact same thing under a microscope. A little speck of dust in a drop of water gets constantly hammered by trillions of invisible, jiggling water molecules, and it makes the dust dance around all over the place. We are literally watching the invisible world push the visible world around. It's undeniable proof. And if this atomic dance is happening to a speck of dust, it really makes you wonder.
So, we've seen how atoms build simple stuff and drive all these processes. But now we come to the most profound, the most mind-bending implication of all this. The atoms that make up you.
You know, this whole journey has been like climbing a staircase of complexity. We started at the bottom with simple repeating grids, like a salt crystal. Then we moved up to these loose swarms of particles, like water. Then we saw simple, violent rearrangements, like fire. Then came these custom, elaborate pieces of architecture, like a scent molecule. But the very top of that staircase, the final step, is life itself. It's these non-repeating, infinitely changing arrangements of atoms, built with a complexity we can barely comprehend, all from the exact same simple rules.
And this leads us to what is maybe the most important hypothesis in all of biology. It's the idea that there is nothing that living things do that can't be understood from the point of view that they're just made of atoms acting according to the laws of physics. Everything you do, everything an animal does, the atoms do. There's no magical separation. The mechanics of physics are the phenomenon of life.
So, is that person you see in the mirror just a big, complicated pile of atoms? Well, yeah. But as the source material so beautifully puts it, when we say we are a pile of atoms, we do not mean we are merely a pile of atoms, because a pile that is on just a repeating pattern, a pile that is always changing, well, that kind of pile might well have the possibilities which you see before you in the mirror. So the question is, what possibilities will your particular arrangement of atoms discover next?